Good morning. Welcome, and thanks for making it to my talk, the last day. So my name is Sharma Podila. I'm a software engineer at Netflix, working on resource allocation and scheduling using Apache Mesos on Amazon EC2. Before Netflix, I also spent quite a bit of time doing resource allocation and scheduling work in a more data center environment at Sun and Oracle. Regardless of data center or cloud, Apache Mesos can be very useful for deploying your applications by doing appropriate resource allocation scheduling. So that's what we're going to talk about. Let me start a little bit with some context on why we're doing this. Most of you are familiar with how Netflix traffic can be quite a bit in terms of scale. At peak, the US download traffic, more than 34% of it is Netflix traffic in the US. And all of this traffic is enabled by a microservices architecture that users come to, and it gives the discovery of the movies and playback. And at this scale, a lot of things can and will fail. What we want to do, one of the things we want to do is detect signals like anomaly detection, service health, etc. And we not only want to detect big signals like how is the overall service health or error percentage in any aspect, but also want to do at smaller permutations. There's a lot of permutations. Also want to detect small signals that are important as well, in addition to the big signals. We want to do it quickly, and we want to do it cheap. The infrastructure to detect signals and alert us should be smaller than the infrastructure needed to run the services themselves, and we want to do it at scale. So in order to do this, as part of the Netflix Edge engineering, we are developing tools to detect and visualize the service health for operational insights. And in order to do that, we're building an event processing system that can let us run queries, faceted queries, on live event streams. And for that, we're building an Apache Mesos framework to do optimal resource assignment for the stream processing workload. So an example of the visualization we may have is, for example, this US map that shows us the service health in the US West and East regions as an example. So it provides an overall summary with some interesting charts at the bottom right. But then users also want to dig into a specific aspect of it. For example, this shows a route summary on various aspects of the edge tier of the microservices architecture. And users want to look at the summary of all the routes, look at the RPS, the latency percentiles, etc. But users may also want to, users as in Netflix engineering who are trying to monitor the various aspects of the service, they also want to look at more specific aspects. For example, how is the service doing for a specific UI, maybe PS3 or Xbox users on these devices in a specific region, or maybe also for a specific movie or a specific TV show. And then they would submit a faceted query for these, and then they can start live streaming the service health and other anomaly detection for that specific facets. So today I'm going to talk about Mantis, which is the stream processing infrastructure we're building. I'm going to answer a couple of questions that are very common when you start using Apache Mesos on an elastic cloud. Well, why use it to begin with? We already have ASGs that are pretty elastic. Maybe they can do the resource allocation based on some CloudWatch metrics. And then for people familiar with Apache Mesos, there are already frameworks available. And then the question is, do you need to develop another one, or can you use a one that's existing? We'll look at that. And then some specific challenges in the cloud. And I'm going to basically spend more time on the framework design, Apache Mesos framework design, and the scheduling problem itself. Just a quick show of hands, how many here already use Apache Mesos, either for test or production? Great, there are some. And anyone here who is writing or intending to write a framework for their workload? Okay, great. All right, so we'll definitely look at that. And we'll talk about Fenzo, which is our generic task scheduler that can be used by any framework. And I'll show you some sample usages. So Mantis is an event processing infrastructure. There are other event processing systems already available in open source, quite good ones. When we looked at those and looked at our specific use cases, we felt that, and the use cases being anomaly detection, operational insights, to improve our customer experience, we felt that we needed to build a system that specifically addresses these. And what I mean is we needed it to be cloud native, be auto-scaling with the traffic that we get. Based on the time of the day of the week, the traffic does vary quite a bit. And we wanted to do optimized scheduling of the resources for achieving what we call stream locality. We'll talk about that. And also we felt that although some jobs require message delivery guarantees, such as exactly once delivery, there are some jobs in operational insights that can trade off these guarantees for increased speed and scale. So for example, if there is a job that is doing percentile calculation, it can handle a slight loss in the data if it can scale much bigger and be much faster. But some jobs do require guaranteed delivery, and there's both kinds. So we feel that the jobs can be allowed to specify what kind of SLAs they need. And the jobs themselves need to auto-scale. So if the traffic surges, there's more data to evaluate, and therefore the job themselves need to scale up horizontally. So all of these needs basically led us to building a new system. Another interesting case for us is that unlike other stream processing systems where a lot of times people are putting the data into a queuing system such as Kafka or others, we sometimes have so much data from the operational aspects that it's not practical to put all of that into a queuing system. Instead, what we do is when the jobs are started, when a stream processing job is started, it sends a subscription all the way up to the actual service instances that are running with a query. And there could be multiple jobs, each with different query. These all get subscriptions all the way up, and then the actual app server starts streaming the data that match that query. So this makes it a bidirectional flow of information, first with a subscription with a query, and then the actual data streaming back. So just to get a big picture before we get into the details, Mantis is the event processing system that uses Fenzo, which we'll talk about, to do scheduling on top of Apache Mesos. And we have one or more ASGs, autoscaling groups, that provide all of the resources on which we're going to run them. So in Mantis, a job is made up of a source, which is where the data is coming from, one or more computation stages, and then eventually a sink where all the data is aggregated and made available to the users of that job. And each stage may have one or more workers. It can horizontally scale. And those are the workers that, or tasks that we're trying to schedule using Mesos. So a quick overview of what Mesos is. There have been resource scheduling and allocation systems available. So one thing that Mesos does very interestingly is that it separates out two related but different concepts of resource allocation and scheduling. So if you have a lot of resources and then you have different use cases, say a batch-oriented workload a service-style jobs workload and an interactive workload, you can allocate resources among them using a single Mesos cluster, and then let Mesos give more and less resources to each of those applications. So it can help you do that instead of completely segregating and bifurcating the resources. It also helps you develop distributed applications easily, where you can be given resources as needed, and then you can release them when you're done using them. It makes it easy to develop such applications. And it simplifies basically running multiple types of applications in the same cluster. Looking at the Apache Mesos architecture, there is a master that coordinates all of the resource allocation. And then all of the resources themselves are running an Apache Mesos slave process. And those advertise to the master what resources are available, how many CPUs, memory, the ports available for networking, disk, etc. And then there are applications written on top of Mesos, which are also called frameworks. And frameworks can register themselves into Mesos, to Mesos master, to get the resources that they can use for launching tasks. And a slave, for example, can run tasks of one framework or multiple frameworks. So there's definitely co-tenancy there. And Mesos uses the concept of containers. It could be Docker container, or it could be even a simple, basic Linux C groups-based container. So that's how basically the architecture looks. So why use Mesos on top of an elastic cloud? For us, there are two reasons. One is resource granularity. Tasks can have various requirements: single core, multiple cores, small memory, large memory, and some may require better network throughput, memory bandwidth, etc. There are lots of instance types in EC2. However, by the time sometimes you pick an instance type that's, say, good for network throughput, you automatically get more cores than you may need. You may need just one core. And then you may have other tasks that are not as network intensive, but need more cores and memory maybe. And then you can actually bin pack them together. So that's one good reason one would want to use Mesos on top of an elastic cloud. And another reason for us is startup latency. Getting a new instance could take a minute, a few minutes. However, starting a new task, it could literally be in a few milliseconds. So that's another good reason. So now that we have a good reason to use Mesos, why develop a framework? There are frameworks available in the open source that people can straight away use for running their applications using Mesos. But there could be some reasons where you may want to develop your own. Mesos did make it very easy to develop a new framework. However, what we feel is that if you develop a framework that needs to scale, be fault tolerant, highly performant, it does require long-term effort. So that's the difference. And scheduling itself can be a hard problem. So we feel that there should be a long-term reason to develop your own framework. Otherwise, it's easier to use an existing open source framework and maybe put in a request for enhancement, or, well, write a little bit of code, do pull requests. That's easier than trying to write the entire new framework. So we had some reasons that were not addressed by previous frameworks, and then we developed our own framework, and I'm going to talk about that. So generally, in a cloud, well, most of you are familiar with this. Well, the slave instances can be ephemeral. They're here, they may be gone, then you don't get the same slaves back. So you need to be fault tolerant as far as handling your tasks that were running there. High availability is important. We're going to talk about how that can be achieved. Autoscaling the slave cluster, this is definitely specific to a cloud. If you're running in an elastic cloud, you don't want to allocate say 1,000 resources, 1,000 instances to your cluster and say that's it. That's for peak utilization. But then you want to be auto-scaling the cluster. And auto-scaling is not a feature of the current frameworks available out there, so that's one good reason for us to develop this. And scheduling itself has other challenges that we're going to talk about. So why is autoscaling a challenge? Why do I talk about autoscaling when, well, there's already autoscaling groups here. So unlike request response-based processing, if you're running longer running tasks in using Mesos, maybe they're batch workload or service style, then you can't really just terminate some instances based on, say, average system load, because that would just terminate those tasks as well. You can only terminate instances that are running no tasks. If you're doing request response, then it's easier. You have an ELB in front of it, and then any failed request maybe can be retried somewhere else, but it's not the same for long-running tasks. So suppose we had 4 instances in our cluster, just as a simple example, and then we ended up with scheduling such that there are 2 tasks on each of them and 2 idle CPUs on each of them. So we are using about 50% of the resources, but none of the instances can be terminated. Whereas if I had placed them differently, such as this, where I still use 50% utilization, but then I can now actually terminate 2 instances. So this is a basic example of why autoscaling is important to consider in scheduling using Mesos. And there could be other reasons. For example, some tasks run long, some tasks run short. And if you end up with a machine where there's 2 jobs that are long running and 2 are short running, when the short running jobs are done, you still can't scale down your cluster because this is still being used by those long running tasks. And then if you were to separate out such that you schedule all the long-running ones in some place and all tasks that have approximately the same completion time into other machines, then you can scale down much quicker. So scaling down is harder than scaling up for this kind. And the other challenge is the stream locality. So suppose I have a data stream coming in, and I have 3 tasks running on 3 different machines. So I now have 3 network connections streaming the same data. Instead, if I had placed those 3 jobs on the same machine, I have 1 network connection that is getting used for the same amount of data. So therefore, reduce network bandwidth, and therefore be ability to scale up much larger. And there are other interesting stream processing challenges. So if I have a stream processing topology of 1 job, which has 3 stages, and suppose the 3rd stage is having trouble. It's slowing down its computation. And then what we can do is detect the slowdown, which is also called as the back pressure, and horizontally scale that stage. So automatically the whole job is flowing smoothly again. So let's move on to the framework design itself. Mesos framework design, if you were to develop your own framework, there's a few things you should consider. One is the availability, and fortunately there's Zookeeper. What we use is multiple instances of our framework are running using the leader election recipe from the Zookeeper service. So that takes care of that. Another question to answer is resource granularity. Using Mesos, you can do a coarse grain scheduling resource allocation or a fine grain. In coarse grain, you would get some amount of resources and then launch multiple tasks into the same executor. This is especially useful if the tasks are very short running, whereas in a fine grain, you would deploy 1 executor per task. And this also gives you a clean separation for resource isolation, and that's the model we use. Task state persistence is important when you're developing a framework, and then Mesos provides a way to reconcile tasks, because your framework may have one idea of what tasks are running, and then Mesos master has a similar picture of what's running. And if your framework were to restart, you can use the reconcile feature to make sure that you haven't lost any task state updates while you were down. There's a checkpointing feature that Mesos also provides, where a slave daemon restart can connect to the tasks that are already running. You would almost always use this feature unless you're testing. I can't think of a reason why you would not. Mesos works with what's called resource offers. So when there is a resource available, it gives a resource offer to the framework saying you can use this many CPUs or memory from this machine. And frameworks then launch tasks using that offer. It's generally a good practice for frameworks to release the resource offers that are not being used, so another framework that's sharing the cluster can use them. So those are the considerations if you are developing your own framework. So let's get into the scheduling. A couple of, high-level objectives are that we want to schedule very quickly, because scheduling can be a compute-intensive problem. And then we have a heterogeneous mix of tasks, resources of different sizes, shapes. And then, well, we want to have some service-level objectives for the scheduling itself, autoscaling, task locality, affinity that people can define between their tasks. And specifically in EC2, we want to do availability zone balancing for tasks. And then also, we want to have plugins because not all optimizations can be, well, designed to begin with, but as you progress and find new ways to optimize tasks, you should be able to put in plugins for optimizations. So we've created a Fenzo, which is a generic task scheduler that provides these features, autoscaling, heterogeneous mix, and also visibility into why tasks are not running. One of the challenges in operations is somebody submits a job, it's not running right now. Well, why is it not running? And it can provide answers like, hey, there's no resource left to run your task, or there are plenty of resources, but you're asking for a resource that's not available. Maybe you're asking for too many CPUs, and there's no such instance type in your cluster to satisfy that requirement. So, and then it provides a way to put in your own plugins for constraints and fitness. So there's a few things I'm going to talk about Fenzo. These are the things, and then let's go into them. Fenzo itself can be used by any Mesos framework. All frameworks eventually get resource offers from Mesos master, and they get task requests from the users. You just feed those two things into Fenzo, and then it gives you a resource assignment based on the optimizations that you want to do. So when we look at the scheduling problem itself, we like to think of it as in these two aspects: how urgent the task is that needs to be assigned some resources, and how well does that task fit on a given resource or a given instance. And if the fitness is near perfect, or if it is very urgent, we'll go ahead and assign that, or we wait for another instance to see if we can find a better fit. That's the general strategy. And scheduling itself, it can be a hard problem, but in real life, well, if you've got a situation where any task can fit on any instance, then it's very tempting to use a first fit model, and that could be really fast. However, you might not be able to do optimizations because you're just using the first resource that's available. And if you start looking at optimization as the perfect fit based on task locality or any other optimizations you have, then it can get computationally very expensive. Even if you're not reassigning any tasks that are already running, it's still pretty expensive. So what we would like to do is stay as close as possible to the first fit assignment in terms of speed, but achieve as much as possible the optimizations. So how do you do that? There's no big algorithm. It's actually very simple. All we do is, for each task, we evaluate its fitness on all the instances that are available. But then we only do it until we find a good enough fitness. So although this loop is very simple, the real work is in these two things. One is, how do you define a good enough fitness? And the other is, how do you define fitness? What is fitness? Fitness is usually defined from 0 to 1, 0 being totally unfit, 1 being perfect fit. And somewhere in between means, well, it fits to some degree. And then there are constraints. Well, let's talk about constraints. There could be two kinds of constraints: hard constraints, soft constraints. Hard constraints must be satisfied. They affect the resource selection. So for example, you have tasks that say, I would like to run only on M1 extra large type instance or another instance. So that's a hard constraint. If you put that, the task will only run on those type of instances. Or you may have a job that says, there's 3 availability zones, I have 3 tasks, and I would like to make sure each task runs on only 1 availability zone. That's a hard constraint. And it has to be met before the job can be assigned resources. And then there's soft constraints, which are, well, same as the hard constraints, except if you find a resource that meets the constraint, go ahead, assign it. Otherwise, give me the best possible. I would rather not wait for the perfect fit. That's the soft constraint. And then this can be used similarly. I would rather run on M1 instance type, but if it's not available, then just put me on the next one that's available. That's a soft constraint. And Fenzo comes built with a few constraints and fitness calculators. So bin packing, for example, if you want to achieve CPU bin packing, or maybe sometimes memory bin packing is more important, that's already available. Then there are a few other constraints available. So we can put in a constraint based on a host attribute. So for example, one of the host attributes could be availability zone. Each instance that's available has an attribute on it saying which availability zone it is. And then I could specify a constraint saying I want to only run on this availability zone, for example. Or you can use that and the instance name itself if you, for some reason, want to only run on a specific instance. And then there's also a unique host attribute constraint, where you're not looking for a specific name for the host attribute, a zone name, for example, but you're saying, I have 3 tasks, and I want to make sure they each land on a unique value for the zone attribute. And similarly, if you want to run 10 tasks, each of them you want to make sure is on a different host. Same thing, you put in a unique host attribute, and it readily gives you that. Another one is exclusive. Sometimes you want to run a task on an instance and have no other task running there. And then there's the other one called balancing host attribute constraint, which balances all of your workload. If there's large jobs, say you have 100 tasks on them, and you want to balance them across availability zones, then you would use this. And each of these constraints can be specified as hard or soft. So if a hard constraint, the job would actually be pending until you're finding a resource that satisfies it. Soft constraint will get it launched quickly and trying to make it fit as much as possible based on your constraint. So let's look at how bin packing fitness calculator works. It's actually very simple. It can be defined as the ratio of used CPUs to the total CPUs if I was doing CPU bin packing. And then suppose we have 5 hosts. Host 1 having no other tasks running on it right now, host 5 having all CPUs already taken for other tasks. Then using this equation, the fitness comes up as 0.25 all the way till 1.0 for host 4, and then it's 0 for host 5 because it can't fit, all the CPUs are taken. And so based on this, if I were to do that simple algorithm that I showed before, I would pick host 4 because it's the perfect fit. So that's how bin packing would work. So, well, does bin packing really help? So here's an experiment that we did. So suppose you had a cluster with 3,000 instances. And well, we did an experiment with testing Fenzo, which means I can actually have the scheduling be tested without requiring all the 3,000 instances. So this shows how the scheduling algorithm would work in that case. So let's say there's 3,000 instances, each having 8 CPUs. And then I have 3 different task sizes, 1 CPU, 3 CPU, and 6 CPU. And if you were to place them not in an optimal way, you can see they will not fit perfectly on an 8 CPU machine, right? There's 3 and 6 CPUs. And then what we do is iteratively, we start filling up the cluster. In each iteration, we launch a few tasks, as if new jobs are coming in on a periodic basis. We ran about 50 iterations. So how does that look? So the left side chart shows you when no bin packing is used. Then some instances are fully used, as in all 8 CPUs are used. Some instances are partially used, non-zero CPUs, but not fully used. And then there's some instances that are empty because, well, we only ran 50 iterations. There's still space in the cluster. When we used bin packing, the number of instances that were partially used was very close to 0. Now, what this means is that, first of all, there's more number of instances that are empty. So I can achieve scale down quickly and use fewer instances. And so this is one way to do CPU bin packing. And similarly, there was another experiment we did with the task runtimes. So we have task runtimes in two categories, short and run for this experiment, short and long running in this experiment. And then when we used bin packing, we saw that almost all instances had similar runtime tasks versus not. So what this means is that when the short running tasks are done, those instances will be freed up, and I can easily scale down. Stream locality, which I talked about, can again be defined very easily in Fenzo. We define it as the percentage of tasks on that host that are already connected to the same stream. And using that, which gives me a 0 to 1, well, 0 to 1 value, I can easily achieve stream locality. And sometimes you want to do more than one thing. Fitness calculators can be composed together. Stream locality is important to me, bin packing is important to me, so I can just combine them together and say one is more important than the other, and maybe give more weight to stream locality and less weight to CPU bin packing. So you can achieve different SLAs using a composition of fitness calculators. So the other part is autoscaling. So Fenzo looks at the resources available, what tasks have been assigned, and then can give you callbacks for scaling up and down. It does that in two ways. One is rules-based. This is similar to how you set up rules for an ASG, where you have a min and a max. So in Fenzo, you can set up a minimum idle that you always want to keep, just in case there's new workload coming in. You don't want to wait to spin up new instances. You want to have some buffer there. And then a max. If the number of idle resources falls below the min, then it gives you a callback to scale up. And if it goes above max, it gives you a callback, not just to scale down, but with a list of instances that can be terminated because they're idle. So as with any scale up and scale down, you need to have a cool down period to do it right. One challenge there is that if there's a sudden surge in incoming requests, and usually scale up happens by some number, so suppose you're scaling up by 10 instances, but the amount of workload that's pending requires 50 instances, you don't want to wait for the cooldown and then scale up again. So Fenzo also does resource shortfall analysis and then can scale up aggressively for pending workload, even if it's in a cooldown period. So like I said, Fenzo can give you callbacks. You can have multiple ASGs. So for example, you can have one ASG that is more ideal for running large memory workloads, another ASG that's for network throughput oriented, or another ASG for CPU intensive workloads. And for each of them, you can define different autoscale rules in Fenzo. And autoscaling itself, well, there's 3 numbers to control in an ASG, the min, max, and desirable. The number that Fenzo gives you is ideal to be set on the desirable number. Max, I would use the max number to limit the scale up for any reason. Maybe you never want to have more than some number of instances in your cluster, budget reason or whatever other reason. And then min is controlled by a more macro level scale up adjustments. So at Netflix we have Scryer, which is a predictive auto scaling engine. And what it does is it analyzes historical usage of a cluster of an ASG and says, hey, during this hour of the day, this is what has been traditionally used, and then it predicts for the next hour based on similar times, previous days, day of the week, etc. So that is a better candidate for setting the min. And then what Fenzo does is it auto-scales up and down based on the current demand between the min and max. So that's the strategy. So a quick look at how Fenzo scheduler itself can be used. So in Java, for example, this is how you would create a scheduler where you just specify very simple things like I was telling you about Mesos offer should be released if not being used. You just tell it how long you want to wait before you release an idle resource offer, and then it just does that for you. And once you create that, you can also say, I want to use a fitness calculator that's already built in. It's the bin packing fitness calculator. And then I can also say, hey, I'm just looking for a fitness to be just 0.5 or greater. I don't need a perfect fit, or you can vary that. And once you do this, you now have a task scheduler that you can feed your tasks into and all of the Mesos offers, and then it'll do the assignment for you. So to summarize, we looked at why Mesos could be a good candidate in an elastic cloud for resource granularity and task startup latency reasons. And Fenzo lets you schedule resources to tasks and achieve customized optimizations. And I showed you how we're building a stream processing system that uses Fenzo to do stream processing for live events to build the data visualization. So I think we have a few minutes. We can take questions if there are. Yes?
So yesterday during the keynote, they announced the container scheduler ECS as the core. And I don't know anything about it, but I saw the demo, and it seemed they're doing bin packing the exact same way.
Right.
Packing as much as possible, so they're doing. Is there any relationship? Are these two separate efforts between Netflix and Amazon? Their container scheduler.
Right. So yeah, the new ECS container service that was announced, was that similar, or was there any work done in collaboration, or these separate efforts? That's the question. These are separate efforts. I learned about it when you learned about it as well. But I think there are some similarities, obviously. But as was mentioned, Apache Mesos can still be used in conjunction with ECS to do more sophisticated scheduling, and the container service would still work with Mesos. So what I'm talking about is more about resource allocation and scheduling. Container service helps you launch the containers that you have using Docker. So that's more of the focus, and we can do more sophisticated scheduling using this. So I think they would work together. They're not one instead of the other.
Yeah, I'm just saying in the demo, they showed the demo of a cluster.
Right.
And then they showed how it was done. And the way it was done, it looked like they were packing the bins.
Correct. Yes, bin packing is what they showed as well, and bin packing could be done in various ways. Sometimes it is CPU based, sometimes it's task locality based, and you can define different optimizations based on your application. Yeah. Yes. The question is, are we open sourcing Fenzo and Mantis? Right now, they're not open source, but in the future, they might be, should be. Yep, thanks. Yes? I'm sorry, I couldn't hear you.
So when scaling down with bin packing, how does that work? When you do which instances it's going to kill off? Autoscaling doesn't tell you which ones it's going to kill.
Correct. So the question is, when you scale down, do you have control on what instances you kill? Well, I'm writing code in Java. The Java interface to the ASG actually does have a way to say, terminate this instance and scale down the ASG by count of 1 by terminating this. So that is the one you want to use. You don't want to just say, set the desirable lower. In that case, it would terminate any instance based on different criteria. So yeah, there is a way to do that. Yes?
Does Fenzo have any understanding of AZs?
I'm sorry, could you repeat that? Does Fenzo have?
Knowledge of AZs, balance things across AZs.
Right, so Fenzo is written as a generic scheduler. It doesn't necessarily know the availability zone names, but it has a built-in constraint that you can say, balance it according to this host attribute. And one of the host attributes is the availability zone name. So, yes. So if I understand the question right, so why does the constraints and why does Fenzo need to be in the framework? Can it be inserted into Mesos itself? Okay. So can Fenzo be inserted into Mesos itself? I think that's a good question. Mesos itself provides resource allocation. It explicitly does not do scheduling. There's a good reason for it to be really fast in resource allocation. So it separates out these two. It expects frameworks to do the actual scheduling, and Fenzo is built for scheduling. But what can happen is Fenzo can be used by any framework, whether it's Marathon, I think you mentioned Marathon, or other frameworks, and we're using Mantis. In fact, at Netflix, we have another framework that's also using Fenzo. Any of them can use Fenzo to make all of this possible. Right now, it's not open source, but in the future, that is a possibility. Yes? I'm sorry, I can't hear you. Uh-huh. I'm sorry, I can't hear all of it. You are asking about scale up and scale down? Who is responsible to start and stop the machines? Okay, so Fenzo provides the framework for doing the auto-scaling. It gives you a callback to say, you need to scale up. That scale up ideally should basically trigger an action into the ASG to scale up, to set the desired number. So that part is not in Fenzo, because that is more logistics of scaling up and down using the ASG, which requires your credentials and things like that. So that's not part of Fenzo. Fenzo provides the generic way of telling you to scale up and scale down. So if you had different ASGs or different clusters, okay. Okay. Right. So I think I understood the question. So if you have 10 machines, and if Fenzo says shut down these 5 machines, or scale down by 5 machines, will it specifically shut down only those 5 or any 5 in the 10 machines? Will it affect other tasks? So what Fenzo does is gives you a list of the 5 machines to terminate, which are idle. So when you terminate those, the other machines will not be affected. The other tasks will not be affected. So when you scale down, you don't want to scale down by telling the ASG to reduce the desired number. You want to scale down by terminating those specific instances. So then it should be fine. Correct. So when you terminate that instance, you're also setting the desired number to go down by 1 for each of them. So that automatically does that. That is an interface into the ASG API. that Amazon has, and then that, like I said, requires credentials and all that is specific to your application. And that is not part of Fenzo. Fenzo only provides the basic infrastructure to do it, not the logistics of actual scaling up and down of ASG itself. Right, right. Yeah, I think I understand what you're trying to say. We are running out of time, but I will be available, so maybe we can take our conversation after this outside. Okay. Thank you all for your time.